Space and time make up the grand stage where the play of the universe unfolds. But this stage is entirely flexible. It bends, warps, and constantly reacts to the matter resting on it. Visualize this as a flexible grid. Placing masses like stars on the grid causes the surface to sag, creating everyday gravitational pull. But when a massive star dies, its core implodes. This extreme density pulls the grid downward into an infinitely deep funnel. This creates a cosmic trapdoor. The event horizon forms an invisible, one-way shell around a region of space that is shielded from the rest of the universe forever. It is a no-go zone where the rules of the stage begin to change. To see exactly where the fabric of reality is stretched to its limit, we have to make a literal descent straight into this trapdoor. Gaining a complete picture of the universe requires investigating the specific points where our current theories of physics are unable to provide an explanation. Approaching a spinning black hole brings you into the ergosphere. Because the dying star that formed the black hole was rotating rapidly, it drags the surrounding fabric of space along at incredible speeds. This video illustrates the ergosphere as a dark, violent cosmic whirlpool. The relentless circular motion of spacetime here is completely irresistible, making it physically impossible to remain still, no matter how hard you thrust your engines. Just outside the event horizon lies the photon sphere. Gravity is so intense here that light itself is forced into a circular orbit. If you hovered in place and looked straight ahead, light reflecting from your back would travel all the way around the black hole to your eyes, letting you see the back of your own head. This proximity also warps the passage of time. The stronger the gravitational pull, the slower your clock ticks. From your perspective, the universe above you would appear to speed up, while distant observers would watch your movements slow to a crawl. If you fired your thrusters and managed to escape back to normal space, you would find that eons have passed. It is a strictly one-way time travel trip to a future where your loved ones are long dead. If you approach a smaller black hole, the physical threat is immediate and lethal. Because your feet are closer to the center of the mass than your head, they feel a significantly stronger gravitational pull. As you descend, gravity pulls you apart. Your body is squeezed thinner in a process called spaghettification, reduced to a thin stream of hot plasma. Getting anywhere near these anomalies requires sacrificing your physical integrity and severing your connection to human time entirely. Crossing the event horizon creates a profound divide in perspective. A distant observer would never actually see you enter. They would watch you freeze and slowly fade away. Meanwhile, the blackness envelops you until your only view of the outside universe shrinks to a tiny spot of light. This map shows how space-time warps inside the event horizon. Every directional arrow bends inward to the central dark circle. Every forward leads toward the center. Escaping only accelerates your downward journey. To survive the longest, you must do absolutely nothing. At the exact center lies the singularity. All the matter that ever crossed the horizon is crushed into a single point, infinitely small, creating a divide by zero error in our current understanding of the universe. Everything that reaches this point loses its past. There is no memory of the original objects. The singularity retains only three properties: mass, spin, and electric charge. Inside this threshold, reality's ultimate eraser deletes all complexity. By trapping this infinitely dense point behind the event horizon, the universe avoids the time travel paradoxes that would otherwise result from information escaping the interior. Looking past the infinitely small physical bottom of the black hole, we find the infinitely distant future of the dying universe. Over eons, black holes will slowly shrink through a quantum mechanism called Hawking radiation. In the vacuum of space, microscopic quantum fluctuations constantly create pairs of particles. When this happens right on the edge of the event horizon, one particle falls in while the other escapes, slowly stealing the black hole's mass. As the mass decreases, this evaporation accelerates. The escaping radiation gets faster and stronger until the remaining black hole eventually evaporates in a sudden flash of high-energy radiation. Imagine an hourglass filled with 1 grain of sand for every particle in the universe. If 1 grain falls every 10 billion years, waiting for all the sand to drop wouldn't even scratch a % of these lifespans. Our best current model, general relativity, is unable to explain the infinite density at the center of these objects. The math simply stops making sense. Black holes represent a primary focus for modern physics. They provide a reason to keep doing science, offering puzzles that will persist long before the last one evaporates.